Thanks for joining me for example 4.3.2. In this example, we're asked to find the points on the sphere x squared plus y squared plus z squared equals 1 that are closest to and farthest from the point 4, 8, minus 1. Let's begin by drawing the situation. If we add the sphere, it's a sphere of radius 1. So let's add ourselves some axes here. There's our x, our y, and our z-axis. And so these intercepts are at 1 and minus 1 on all of the axes. It's easy to check that our point here, 4, 8, minus 1, if you plug it into the equation, square those and add those all up, you're going to get a point that's not on the sphere. So let's plot that point approximately there. The scale's not perfect, but we get the picture. If that's the point 4, 8, minus 1, we're looking to find points on the sphere that are closest to and furthest from. So if we let a point x, y, and z be on the sphere, we are looking to maximize and minimize the distance from x, y, z to the point 4, 8, minus 1, or the square root of x minus 4 squared plus y minus 8 squared plus z plus 1 squared. Now, optimizing with a square root is algebraically a little cumbersome, and it works out to be the same and algebraically a lot easier to maximize or minimize the square of the distance. So we're going to maximize and minimize our function d of x, y, and z, which will be the square of the distance. So x minus 4 squared plus y minus 8 squared plus z plus 1 squared. Now this function, this distance, is going to be subject to a constraint. Our points x, y, and z need to be on the sphere, so they have to satisfy this equation. So let's call that equation g of x, y, and z, which is x squared plus y squared plus z squared, at a point where, or at a level, where the function g is equal to 1. This is the setup that is perfect for Lagrange multipliers. So let's get started by calculating the gradients. The gradient of, let's start with d, at x, y, and z. So we're taking the derivative of this expression, which is going to involve a chain rule. So 2 times x minus 4 times 1, plus 2 times y minus 8 times 1, right, the derivative of the inside, and 2 times z plus 1 times 1. The gradient of g, taking the derivatives of this expression, so 2x, 2y, and 2z. Applying Lagrange, we are going to have the gradient of d being lambda times the gradient of g, and we have the equation g of x, y, and z equals 2k. That is our system of equations. So let's write our gradients equal component by component. So you can see that if we start out by saying 2x minus 4 squared is lambda times 2x, well, we can cancel out those 2's, and which I'll just write at the beginning for the next components without the 2's. So y minus 8 is lambda times y, and z plus 1 is lambda times z, with the constraint equation that x squared plus y squared plus z squared is equal to 1. There's our system of equations. If we isolate x, y, and z in each of these equations, so x minus lambda x is equal to 4, if I factor out an x and divide, I'm going to get that x is 4 over 1 minus lambda. Similarly, here I will get y minus lambda y is equal to 8. So y is equal to 8 over 1 minus lambda. And lastly, here I will get z minus lambda z is equal to minus 1. And so z is minus 1 over 1 minus lambda. If I take all of these and plug them into my constraint equation, I should be able to solve for lambda. So we're going to have that 4 over 1 minus lambda, all squared, plus 8 over 1 minus lambda, all squared, plus minus 1 over 1 minus lambda, all squared is equal to 1. I'm going to multiply up 1 minus lambda squared. So I'm going to be left with 4 squared, which is 16, plus 64, plus 1 is equal to 1 minus lambda quantity squared. 16 plus 64 plus 1 is 81, is 1 minus lambda squared. And so plus or minus 9 is 1 minus lambda, or lambda is 1 plus or minus 9. So there are two possibilities, which is convenient because we're looking for 2 points, the closest and the furthest away. So we're going to have lambda is 1 plus 9 is 10, or lambda is 1 minus 9 is minus 8. Going in to find the x, y, and the z. X is 4 over 1 minus 10, or minus 4/9. Y is equal to 8 over minus 9, or minus 8/9, and z is minus 1 over minus 9, or 1/9. Let's move these maybe a little out of the way so we have a little more room. At lambda is minus 8. We'll plug into the same equations, and we'll get that x is 4 over 1 plus 8 is 4/9. Y is equal to 8/9, and z is equal to minus 1/9. To see which of these is the minimum and which is the maximum, we need to evaluate in the d function. So we'll take d of minus 4/9, minus 8/9, and 1/9, and I calculated that off screen, and I got 100. And d of the other point, 4/9, 8/9, and minus 1/9, I got 64. Now you might have guessed that this would be the closer point because it's in the same quadrant as or the same octant as the point that we were given. But regardless, calculating it is the official way to go to check which is the smaller and which is the larger. Now, there is some question for any function as to whether the extrema that are the solutions you get out of the Lagrange system are actually valid. And here they are because we know that the sphere is closed and bounded. So because the sphere is closed and bounded, the EVT guarantees us, because our function is continuous, it guarantees us an absolute max and a min on the sphere. And so the Lagrange solutions are the two solutions that we are looking for. The point 4/9, 8/9, and minus 1/9 is closest to our given point, and the point minus 4/9, minus 8/9 and 1/9 is furthest.